A point P is chosen uniformly at random inside an equilateral triangle ABC. It's a geometry problem, so the first step is to draw the figure as accurately as possible. This is not the best, but I think it will do. Let's read on. The probability that angle APB, angle BPC, and angle APC are all obtuse can be written as this thing, and where A and B are positive integers, find A plus B. So we are picking a point randomly inside this triangle, so point P, and the triangle is triangle ABC, and we're looking at angle APB, BPC, and APC, and these are this angle, so that's the first one. And the second angle is angle BPC, so that's the second angle, this angle. And the final angle is APC. And we want to make sure that every single one, all three angles, are obtuse. For this particular case, it looks like we have every single angle being obtuse. But if you move P upwards, so if P was right there instead, then it's pretty easy to see that angle BPC is going to be acute because angle BAC, this angle is 60 degrees. So as this point P moves towards the point A, we are going to get an acute angle eventually. So our condition is not going to be satisfied for every single point P. So let's think about how to break this question down. But before I go on, I want to recognize Kevin M for being the very first person to correctly answer this question with the answer of 9. A huge shout out to Kevin M. So how can we approach this question? Before we start, it's going to be extremely beneficial if we know this one theorem from geometry. And it states, I'm not sure if it has a name, given a segment of length AB, and we're picking a point in the plane, and let's say we have the circle with diameter AB centered at the midpoint of segment AB, so that's a circle, and it can be proven, and if you have not proven this yet, I highly encourage you to. If a point is lying on the circle, then we are going to get 90 degrees. If the point is located inside the circle, we are going to get an obtuse angle, so that's going to be obtuse. And if a point is outside the circle, you guessed it, it is going to be acute. So this one is now going to be acute. So using this fact from geometry, now it's pretty easy to find the region that we want. In this case, easiest way of drawing a circle is to connect the midpoints of the sides to draw the congruent medial triangle, and we know all four of these triangles are congruent. They can also be easily proven. And why am I doing this? Well, we want to make sure every single angle is obtuse or inside the circle. So we want point P to be lying within the circle with diameter of AB. And realize that by drawing this medial triangle inside, it was easier for us to sketch the circle because we know the circle is going to pass through this point and this point, because all four of these lengths are equal. So we know the circle has to pass through this point, and also using the same reasoning, our point P has to be inside this circle, if I can draw it correctly, inside this circle passing through the midpoint, and finally our point has to be inside the circle with diameter BC, so the one that should go something like this. So we want to find the probability that a point P picked inside this equilateral triangle, so inside the large equilateral triangle. So when you're picking a point P inside this, we want to find the probability that it's also going to lie within this region. So we want to find the probability that point P is in this red region. So how can we find that? Well, all we have to do is compute the area of ABC and the area of this region. And it's going to be easier for us to deal with that if we let the side lengths of the entire equilateral triangle be 2. So the circle has radius of 1. And of course, we have the symmetry, so everything is going to be proportional. So picking 1 and 2 is not going to change our answer. The general case is going to work the same. Anyway, what's the area of the entire triangle? So what's the area of the entire sample space? Area of ABC. Well, area of an equilateral triangle, so area of equilateral triangle, is s squared times square root of 3 over 4. And in this case, the side length is 2, so 2 squared times square root of 3 over 4 gets us square root of 3 for the area of the entire sample space, or area of triangle ABC. Now, how do we find the area of this weird shaped region inside? There are many ways of approaching this. Perhaps the most elegant way is to exploit the symmetry of the situation, and this is going to be easier to see if I draw a larger diagram. So here's the area that we want to find. We have this equilateral triangle inside. So here is an equilateral triangle, and we have these 3 circular segments bounding it. And we want to find the area of this region. Well, one way of doing it is by finding the area of this circular sector. So we can find the area of this thing, and we can add that 3 times. So we can add it once, add it twice, so add it twice, then add it one final time. So basically we're finding the area of one circular sector and multiplying by 3. Then we are going to get the area of the entire thing, except we are overcounting the center part, except we're counting this part 3 times. So one way of finding the area of the entire thing is to multiply that area of the circular sector by 3, which is what we have, but take away the central triangle twice. So take away the central equilateral triangle twice to only count it once. And what is this going to get us? Well, the area of the circle. So the area of this entire circle. So this circle with radius 1 is pi, but we only care about the part with angle of 60 degrees. So that's only 60 degrees, which is 1/6 of 360. So the area of the circular sector is going to be pi over 6. The entire circle is pi. If you're extending the circle all the way, the entire circle is pi. We only care about the 60 degrees part. And what's going to be the area of the equilateral triangle? Well, it has a side length of 1, because that's also an equilateral triangle. So we know it's going to be square root of 3 over 4 using this formula, plugging s of 1. And this is going to get us pi over 2 minus square root of 3 over 2. And now we can find the answer. But before we do that, I want to point something interesting out. There is a name for this special shape. There is a name for the region that we wanted to find, and that is Reuleaux Triangle, if I can spell it correctly. So Reuleaux Triangle. I'm not quite sure how to pronounce it. And you can also get this triangle when you're intersecting 3 circles. So if you have a Venn diagram with 3 equivalent circles intersecting in this way, then the central region is going to be Reuleaux Triangle. And also, it can be proven using the same technique we just did. If the inside equilateral triangle has length of r, then the area of this entire Reuleaux triangle is going to be r squared over 2 times pi minus square root of 3. And we see that in our case, the radius, or this side length r, was simply 1. That was the side length. And we also see that our triangle, how it's shaped. So our triangle ABC is really this triangle inside. So here is our triangle ABC. Anyway, let's finish the question. So we want to divide the area of the Reuleaux triangle, so pi over 2 minus square root of 3 over 2, by the area of the entire triangle ABC, which is square root of 3. So we're dividing, and we're going to get, so we're dividing by 2 times square root of 3. On top, we have pi minus square root of 3. And we want to rationalize this because b is an integer. So let's multiply by square root of 3 to top and bottom. And that's going to get us pi times square root of 3 minus 3 over 6. So this is a and this is b. So we have a of 3 and b of 6. So we know a plus b is 3 plus 6, also known as 9.